Okay, hi everyone. I'm Zongrui. Today I'm going to talk about the jungle of this micro, also three-sheet micro tuning. This talk is about differentially private approximation on graphs. Okay, so why we care about privacy in graphs? And we all know graph-related data structures are widely used in industry, and most of them are weighted. For example, in some music app, there is a bipartite graph that is used for modeling the user preference for different artists and albums. And in this case, there is a list of artists and a list of users, and the attribute will represent the user preference to the corresponding artist. Okay, so in many real applications, the property for these graphs that usually draws critical concern is the cut. For example, a data analyst might be interested in how much a specific user favors a specific kind of artist. And that can be equivalently considered as asking the size of some given SD card in the graph. And this information are naturally sensitive. Okay, so from now on, we consider undirected graph on vertices with n edges and always are positive. Okay, so one of the perspectives to protect the privacy from any type of data analysis, for example, asking the size of some given SD cards, is to output a private copy for the graph, namely a synthetic graph through some mechanism M, and such synthetic graph can be used for further analysis. Okay, so for the privacy part, we want the mechanism M is differentially private. I will introduce what it is later. After we have this, you can learn anything you like from the synthetic graph without any compromise of user privacy. And for utility occurs, we would like the output graph preserve some captures or other combinatorial properties of the graph, like max cut or min cut. Okay, so in order to study private graph analysis, let me briefly introduce the privacy I'm going to use. Okay, so the mechanism for outputting a synthetic graph is differentially private if for any neighboring graphs that are close to each other, like G and G prime, the output distribution should be similar, and the similarity is measured by these two parameters, epsilon and delta. Okay, so in particular, if delta is 0, we see such mechanism preserve pure differential privacy. So it means that the infinity norm of the multiplicative difference of two distributions is bounded by something related to epsilon. And here S is any element in the support of the distribution, of the output distribution. Okay. Also, and if we do not specify privacy parameters epsilon and delta, we just set them and their conventional value where epsilon is some small constant and delta is the inverse of a large polynomial in N. Okay, and you can see that the definition of differential privacy relies on the neighboring data sets. And here we define two graphs are neighboring if and only if they have a difference in only one edge, in the edge width in only one edge by one. So which is the most standard notion in this language?
Sorry, what does by one mean? Like the difference in weights is also at most one?
Yeah, the difference in the edge width is at most one. Okay. So have note that this is no weight level of privacy. That is, we allow two neighboring graphs to have different topologies. Okay, for example, in this graph, if there is a non-edge, we just consider it as an edge with weight 0. Okay, so one example is that like it protects whether user A sends a new message to user B, because it will be a new interaction if the edge will increase by 1. And the goal of differential privacy is to make any pair of neighboring data sets indistinguishable from just reading their outputs. Any question about the definition? Okay, so before proceeding to the next step, I'd like to introduce some basic mechanisms that can be used to achieve differential privacy. Okay, the first one is exponential mechanism. This is a well-known mechanism in differential privacy for outputting discrete candidates. You know, suppose you want to output something given on a graph, like for example, you want to output the min cut, but you cannot directly output the min cut because it's not private. So we define a cost function f to describe how close is it from the mean cost. Alright, so the exponential method says that if t is the set of potential outputs, for example, all possible costs, and suppose the attached utility function is Lipschitz in terms of adding or deleting an edge, then sample from this distribution decided by the utility function and the sensitivity is epsilon differentially product. Okay, so you can see there is a trade-off between the utility and the privacy. So if epsilon is 0, then it is equivalent to just a uniform sample. So it is perfect privacy because it does not depend on the input at all, but the utility is bad. And if the epsilon is infinity, then it exactly outputs one of the costs that minimize the utility function. Okay, so another mechanism is used for outputting continuous value. So it is kind of something special version of the exponential mechanism in the continuous space. It says that for any two input graph or two data sets, and if you want to output a vector value function, and suppose that for any pair of neighboring graph, the L1 norm of G of 1 minus G of 2 is bounded by some constant, we call it sensitivity, and then you just add in independent random noise from Laplace distribution to every coordinates, according to the sensitivity and the privacy budget epsilon. And the variance of the Laplace distribution is decided by the epsilon.
So when you write delta G, that's not the Laplace.
Delta G is just some constant. Okay, so now let's go back to class. Okay, so classic problem about cost approximation is to output the sizes of all costs by a syntactic graph. Okay, in this problem, we want to output a new graph G hat such that any ST card query on G. So a ST card query is just asking the size of ST. So any ST card query on G can be approximated by asking the same ST card query on G hat, and the error can be bounded by some additive error beta. And this is probably one of the most popular problems in project graph analysis and study with Gupta-Rose and Allman tool.
These are not bipartite graph.
This is not what?
Not bipartite.
No bipartite. Yeah. So S and T is just any set of vertices. Okay, so and for generated graph, this problem is recently closed by a series of previous work giving a square root mn over epsilon additive error. So in the worst case, the error for approximating all costs is lower and upper bounded by about n to the 3/2, which is pretty large. Okay, so the previous slides are trying to tell you that we already know how to approximate all costs. So it is very natural to look at another perspective of cost approximation from optimization. That is, if we only interested in some specific cost, like minimal cost or max cost, can we have a better error compared releasing all costs, which is basically n to the 3/2? So if it does, what does the tight error bound look like? So in this talk, we look into minimal cost and separates the graph into at least the k kinetic components. Okay, so next I'm going to recap some definitions on such mean cost that we started with, and both of them are somehow fundamental in combinatorial optimization. Okay, the first one is Multiway cost. Still given an undivided graph and a set of k nodes known as terminals, say T, we want to find the set of edges with minimal edge weight that separates all terminals in T. Okay, so in this case, the minimum cost to separate T is just the isolated cost on one of the terminal. And as you can see, when T is 2, it's just the mean ST cost. And when K is at least 3, finding exact Multiway cost becomes the QR. Okay, so another highly related definition is global K cost. So again, given a weighted graph, we would like to remove minimal edge weights to separate the graph into whatever K kinetic components. Okay, so when K is 2, it's just a normal mean cost, and this is case of K is 3, and the set mean cost is 4. Okay, so now we are ready to define the problem. A little bit different from releasing all cards. From the perspective of optimization, we would like to output a card in the form of a K partition of the vertex sets. And we hope the size of the card specified by this partition is as small as possible. And the utility is measured by a multiplicative error alpha and additive error beta. And OPTG here is the size of the real mean card on G. Okay, so both type of mean card was considered in private literature before us.
I'd like to ask about the problem again.
Okay.
So I'm not sure I understand right. So we're given a graph, and we're asked to output the min cod. So we don't want to actually output the min cod because that would reveal too much information about the graph.
Yes.
So we want to output a cod which has a value which is close to the min cod, but is differentially private.
Yes, exactly.
And that's the problem.
Yeah, that's
Because I think okay, so that sounds good.
yeah.
Wait, is the goal to output just the min cut or to output a graph?
No, you are not going to output graph, you just output a cut. Yeah, so it's kind of like you just output, like for me as a cat, you just output a set vertices. It's enough.
So do we have terminals?
Yeah, terminal is the input.
Okay.
Thank you.
Wait, so what terminals are we considering? What?
But like for multiway color, you have you are going to separate all terminals. Right?
Oh, okay.
Yeah, so it's in the input. It should be.
Okay, that's in the graph.
Yeah.
Just so many sense.
Yeah. Okay. So here's some like previous work for private multiway cards. Hsu et al. Studied privately solving linear program, and by formalizing the multiway card into linear program, we could get a multiplicative error box around 1.3, which is given by some non-private rounding speed. I have to mention that this is also the best known ratio for non-private approximation of multiway cards when k is larger than 2. Okay, and recently, Delaware et al. Gives an efficient and private algorithm with 2 approximation and additive error about only n log k squared instead of n to the 3 halves. So you may see that if we omit the multiplicative error, this dependency of error on n is already better than that of the error we have to suffer for releasing our cards, since it is only linear in n. However, the multiplicative error is worse. So, and for general key cards, when k is 2, Gupta et al. Use the exponential mechanism to give an only log n error. And this comes from a clever analysis of exponential mechanism by using calculus bound on the number of approximate mean cards.
There's no alpha. Like alpha equals 1 or something?
So in this, because, alpha equals 1, because like mean card is not in p file. So and the logarithm dependency is also necessary. So there is so I use the theta notation. However, people do not know what is the type error bound when k is larger than 2. Okay, so first we look at multiway cards.
Sorry, k specifies like the size of the card. What is k here?
K is you want to separate the graph into k kinetic, at least k kinetic.
Oh, and the card is between these. Okay, I see.
Yeah.
That makes sense.
Like k is just normal mean card, right?
Okay.
So so we first look at multiway cards. So based on the literature, a very natural question about private multiway card is that for any fixed k, could we have an efficient algorithm that both has the best known optimal additive error and the best known non-private approximation ratio? And to achieve best optimal additive error, the error should be at most linear. Okay, so in this talk, I'm going to show a positive answer to this question. Okay, first I'm going to show that how to design a private algorithm that achieves around 1.3 approximation ratio and all the additive error for any fixed k. So the 1.3 approximation error comes from the the 1.3 multiplicative error comes from the approximation algorithm, no matter whether there is a privacy or not. And the additive error is caused due to privacy, and for the privacy cost, so does the linear dependency is good enough? The answer is yes. So for the lower bound set, we show that any pure differential equality algorithm for multiway cars has to suffer at least n log k additive error. And this is optimal because it is already matched by the non-efficient exponential mechanism.
So that algorithm, sorry, for the lower bound, the algorithm is not required to be polynomial-time.
Yes.
So it could, I see. So then there's no there's no multiplicative factor because you could solve.
Yeah,
exactly.
there's no multiplicative factor because you are allowed to run like exponential. Okay, so and this is matched by the non-efficient exponential mechanism. So okay, so for any constant k error from the particle state types, and of course the upper bound still has a multiplicative gap from the optimal error algorithm, because we are somehow solving an NP-hard problem. So in that sense, our algorithm is already tied in terms of privacy. Yeah, unless one day NP becomes equal to P, so.
Can I ask Sure. So, I don't know anything about this, but can you make hardness assumptions that would then let you prove a lower bound, like, of a 1.3 times opt plus? Like, stronger than P doesn't equal NP. I don't know how strong it has to be, but is that a sort of thing people study?
Yeah, but I think then it has nothing to do with with the privacy. Like you can just let epsilon be infinite, and you can prove it. Okay. So next I'm going to introduce some intuition behind the algorithm. Okay. So since we are using the edge level differential pattern I just defined, so a neighboring graph could have a difference in all the n to the 2 pi vertices, right? So since everywhere could have difference, a very direct approach is just to add a random perturbation on any pair of vertices. Usually we use either Laplace nodes or Gaussian nodes to preserve privacy, and that is to overlay a complete Gaussian graph, and its edge weights are just ID sampled from some Laplace distribution whose variance is decided by the price project. Okay, so by the Laplace mechanism, it is clearly private, but since it can be used to also output the synthetic graph, so the n up to 1.5 additive error for cut is basically inevitable. And also it may introduce negative edge weights, which makes many approximation algorithms notably killable. Okay, so to overcome both issues, we follow a very well-known construction that formalizes the multiway task problem as a task of simplex embedding. No, we consider simplex polynomial delta k, which includes all k-dimensional non-negative vectors whose L1 node is 1. So this is basically a probability simplex. Okay, so we can associate a vector in delta k for each vertex in the graph. And for the terminals, we just let the vectors associated to them as the set of k bases in the k-dimensional space. Okay, so then to finding the multiway color can somehow be relaxed into finding an embedding of all these vertices into this simplex delta k. That minimizes this objective function, because you can verify that when all x-rays are just 0, 1 integer vectors, then such embedding exactly corresponds to a solution for multiway class. And the edges, the sum of edges crossing different components is just exactly the value of this object function. So if all edges are non-negative, then we can remove the absolute values by some standard trick like substituting variables, and then it just becomes a linear program with simplex embedding constraints. And also there is a rounding procedure for this linear program that achieves about 1.3 approximation ratio. And this is also why a previous work for privately solving linear program achieved this ratio, but a large additive error.
Wait, how are you converting this into a linear program?
Okay, so there is like absolute values, right? Okay, if you want to replace this, you just for example, I can define some new variables z equals to this absolute value, and because this is minimization, I can add some new constraints like Z is larger than XU minus S3, and Z is larger than minus S3 and minus S3. And yeah, so this is minimization, and the additive is positive, so this is equal to the previous program.
Oh,
Yeah.
So what in general is like the goal here or happening? I'm just like a little confused. So like previously you said one way to do this differential bias analysis is like to throw in random edges and then compute.
Yeah.
But that doesn't work well. You get a pretty bad approximation.
Yeah, sure.
So like what are we doing here? Like
Yeah, because here, okay, I'm going to mention it right away. Yeah.
oh, it's happening. Well, I understand.
Yeah, it's happening. So I'm formalizing the multiplicative interlinear program, right?
So can you say like sorry?
So I'm formalizing the multiplicative problem into a linear program, right?
Okay.
Yeah. So next I'm going to solve this linear program privately.
But you're gonna add noise into the way you're solving the program or something to the variables themselves. Or? I don't know.
Yeah. So I'm going to.
I'll wait.
Yeah, I'm just going to mention it in the next slide.
Okay.
Okay, so like the replica is just how to solve this linear program privately with the smallest possible error. Ideally linear in N. Okay. Then we just use some rounding scheme as post-processing, and it does not substantially increase the additive error. Okay, so so formally, suppose X star is some legal fractional solution in the simplex LP, and we recall that for any graph, the simplex LP has the same constraints, right? And let's let X be any possible fractional embedding or any possible feasible solution to the linear program. And the goal is to like add some randomness to the linear program, such that for finite neighboring graphs with a slight difference objective functions, the ratio that the probability the output sim X star is bounded. So this is from the definition of differential class, if you remember that. And we want to bound this for any X star. Then we can preserve privacy. So of course we can just add the random nodes to each coefficient WE. And everything else just follows post-processing. But it is equivalent to just overlay a complete Gaussian graph complete Laplace graph in the input graph, and which has the issues I already mentioned. Okay, so and it is bad because number of nodes is you have to add is like n squared. Okay, so recall that we just want to privately output a cut instead of the whole graph. So it's plausible that we could add much less noise. Then how do we do that? So if you remember that one issue of perturbing everything is that it probably introduces negative edge weights. And if you have polynomial size of negative edge weights, then this program is not polynomial solvable anymore. Okay, so but an observation is that if the coefficient in the terms between any terminal and a non-terminal is negative, it is totally okay. Because since the L1 distance between some terminal and any point in the simplex can somehow be written without the absolute value. Okay, so it's very interesting to think about this question. Can I only add noise between terminals and non-terminals? And another benefit to do that is that if you add noise in that way, the total number of noise is just nk, which looks good enough. Okay, so it's adding noise only between terminal and non-terminal good enough for privacy. Okay, so next I'm going to show that the answer is yes, it is private, even though we do not perturb everything. And also, okay, so the idea of proving this fact can be summarized in one sentence. Somehow we are able to transfer the difference in any pair vertices into the difference in only like edges between terminal and non-terminals. So any noise between them is enough. And to prove this fact, we are actually analyzing what would happen if we shift the noise a little bit according to the so-called correction coefficients. And so we are kind of like analyzing correlated noise, but it's not like I'm adding correlated noise in the algorithm. It's more like I will construct some coupling between the randomness of the noise for parallel neighboring graphs. Okay, so to explain this with to explain what these sentences mean, let's consider a parallel neighboring graph with a difference in between the on the additive between u and v, and both u and v are non-terminals. So this is actually the only non-trivial case, because if both u and v are terminals, then no matter how the additive change between them, it won't affect the optimal solution at all, right? So if value u and v is terminal, then it is already private because we are adding noise between them. So when both u and v are non-terminals, this is the only interesting case, and there is no noise between them. And we still want to show its priorities. Okay, so recall that this is just the objective, and I just omit the constant before it. And the left part is the original simplex embedding objective for the graph, and the right part is all the noises. All the noises I'm just adding. Okay, so and we use G1 and G2 to denote the objective function of this pair of neighboring graphs, where G2 has an extra edge between u and v. And from now on, let's isolate all the noisy terms related to only these two nodes u and v, which is this part behind hx. And hx is just everything else in this objective. Okay, and so G2 is just G1 plus this extra term SU minus SV. Okay, so this is for one side BP. The other case is to remove an edge to get G2, but the analysis is kind of similar, so we only look at this case. Any questions? Okay, so we call that the goal is to bound this ratio, giving any possible functional value.
So maybe I'll ask a question. What's it in mu1 and mu2? Is that for represent two different graphs, like G1?
Yeah, mu1 is
solving this program for. Okay.
Yeah, mu1 is a probability that algorithm output X star on G1, on input G1. And mu2 is a probability for putting X star on input G2. Yeah. Okay, so suppose X star minimizes the function for G1. And the main idea of our so-called correction coefficients is to show that I can always find a series of coefficients ATW such that if I shift the noise according to this coefficient, then X star also minimizes G2 with this actual term SU minus SV. So intuitively, it's kind of trying to cancel off the effect of this actual term and making the optimal value unchanged. So I also emphasize that when I say find such coefficients, I'm not mean by designing an algorithm to find the coefficients because the algorithm cannot know X star, right? So this ATW I just use for analysis, and you will see that just to show the existence of the coefficients is enough for privacy. Okay, so what does it imply? Why do I need these coefficients? For the sake of simplicity, we assume both linear program for G1 and G2 has unique solutions. It is fine since the linear program could have a unique solution almost surely if we add some negative or random perturbation on them. Okay, then I will define two variable sets S and S prime in some high dimensional space. Okay, we see that if the graph is given, the solution to the LP will depend on the randomness of the noise, right? So the meaning of S is just the collection of the values of the random noise, such that with this noise, the optimal value of G1 is achieved when X equals to X star. And similarly for G2, I also define that when the noise takes values for S prime, I define it as when the noise takes values in S prime, then X star is the minimizer of G2. So this definition is totally deterministic and it does not depend on the randomness of the noise at all. And also, of course, and S or S prime can be empty sets. Okay, so directly studying the structure or properties of S or S prime can be very difficult, but luckily with the power of correction coefficient, somehow we can compare them very easily. This is how we do that. So by the promise of these coefficients ATW and ATV, we see that for any noise that ES, when it is equivalent to that X star minimizes G1. So if I add correction coefficient to them, it will become a part of S prime, right? Because it makes G2 also minimized by X star. So this tells us that if I translate S by this vector A, so vector A is just the vector of this correction coefficient. If I translate S with A, then it is a part of S prime. So by the definition of S prime, probability of Z in S prime is just mu2 S star. So this gives us this inequality, and this gives like a lower bound of mu2 X star. Okay, so it might be still very hard to guess what I'm trying to do. Okay, so okay, here's the second part. And on the other hand, if the noise are come from Laplace distribution, then there's a very natural bound between probability of Z in S and the probability of Z in S plus A, right? Because it comes from basic Laplace mechanism. So if suppose A is like with some bounded L1 node, then by the Laplace mechanism we just have this inequality, right? Right, and the epsilon is decided by the scale, so by the L1 normal of the vector A. And again, by the definition, the probability of Z in S is just a mu1 X star. Mu1 X star is the probability that the algorithm on G1 of output X star. Because the randomness of the algorithm entirely come from the randomness of the noise. Okay, so you see that if I combine the two steps, it essentially already gives the upper bound of mu1 X star over mu2 X star. And it is upper bounded by to the power of epsilon. Okay, and for the lower bound side, you just need to do something very similar, but another way around by adding correction coefficients to on G1 and somehow to simulate the effect of this asterisk. Okay, so apparently there's still something missing from the flow trick. That is, we hope the coefficients are bounded in terms of L1 norm so that we can use Laplace mechanism. And indeed, we are able to show that for any fixed embedding, there are correction coefficients with whose L1 norm is bounded by K. And this when cover how to prove this, but I prepared some example to illustrate some intuition behind it in the extended version of this talk. So if anyone is interested, always we'll have some time we can go through it.
But this doesn't help us enough because we need that there exists correction coefficients that work for any X star, right?
Yeah.
Okay, so we're gonna use that?
No, we do not need a unibound. So
okay.
Yeah, so because this is like I'm trying to show that for any X star, I have this.
Okay, I mean, yeah, you definitely have to start from this, right?
Yeah, but it's like I'm going to show some like a probability ratio. It's not like I'm going to use a unibound because I'm not going like to bound some probability.
Right.
Yeah. Okay. So, okay, but also you should have much clear understanding of this as me. So, from a very high level perspective, suppose we want to output some value of function f of all edges. And now suppose I change the input a little bit, like adding a new edge. The function f is not private because now I have a different output x prime because of the change. Okay, now here I use the blue part to denote the edges only between terminals and non-terminals. Now trying to think about our early argument, but in reverse. If I remove an edge, somehow I can just adjust the edges only in the blue part to cancel off the effect of such change, and the output is still expand. So now if you look at these two graphs, they only have a difference in the blue part, and everywhere else outside the blue part is the same. Okay, so somehow we can just add noise. So add noise in the much smaller blue part to preserve privacy. This is why I was saying that we are doing something like transferring the difference to reduce the number of noise we have to add.
In the correction coefficients, your upper bound L1 norm by k.
Yeah.
If you upper bound it by nk, is that still sufficient?
Okay, I'm going to talk about it right away.
Okay,
In
awesome.
this slide. Yeah, this is a very good question actually. So all right. So this for the privacy analysis. How about the utility? Okay. So because that for the previous analysis, we are adding just the standard deviation of the k, right? So and if you want to find the functional Multiway cut from the noisy graph, we see that one possible cut may have as much as all the nk number of noises. So yeah, as George just mentioned, the size of each cut could have additive error at most nk squared. Because the number of noises is nk, and so like the standard deviation is all k. So it is fine because like the linear dependency is already but this guarantee of utility is still very unsatisfying because it is non-trivial only when the error derivative is larger than k. You know, sorry. Okay, but you see that we just want to output a minimal cut instead of like approximately almost a cut, right? So somehow we can use this to further improve the utility and achieve like nk additive error, and that's really silver k factor, and actually it does. So, and the best way to think about it is that instead of considering minimize the mean cut, we actually could look at maximizing on cuts, right? So it's like I'm looking at the dual problem, and somehow in the dual problem, I have much less noise compared to look at the primal problem. And I'm going to show you a toy example to explain why it works. Okay, so now we look at an example of a star graph. And in this star graph, there is only one terminal, only one non-terminal U and like T terminals from like T1 to Tk. Oh, sorry, K terminals from T1 to Tk. And it's pretty easy to verify that each Multiway cut in the star graph have k minus 1 edges, right? Because you have to move this many of edges to disconnect all terminals. So each cut includes k minus 1 noises, and if you use trivial analysis, the error is k squared because sensitivity is k. But you may already found that minimize the Multiway cut is exactly maximizing the weight of the edge that you want to keep it in the graph, right? So clearly, it's just like a reporter max over k candidates, and each end contains only one noise. So this is why we can save a k factor for the star graph. That makes sense? And sure, we can also apply this idea to general graph. The reason we can do that is because you can observe that according to our algorithm, the noise actually form a complete bipartite graph between terminals and non-terminals, right? So, and the result, the noise is bounded to be very dense in each Multiway cut because if you want to separate one side in a complete bipartite graph, you have to remove at almost every edge in this bipartite graph. So except only like you can keep very few of them as in the on cuts. So for the privacy, it is better to consider the dual problem about on cut instead of trying to minimize the cuts, which gives you better utility. Any questions? Thank you. So in conclusion, for multiway cards, we give NK additive error for solving simplex LP by new analysis, and we also give a type pure DP unlog K lower bound for multiway cards from basic packing arguments. Yeah, but I won't cover about this lower bound in this talk. Okay, so the next result is about private global K cards. But I guess I won't have enough time to go into details, but I would like to just show the results. Okay, so we already know that for mean card there is a log K error algorithm by Buka et al. But what should be the correct error when K is larger than 2 for private minimal K card problem? Okay, so to answer this question, first we show that we could get a K log n lower bound on private outputting a K card. And when K is 2, it just reduces to the bound for private mean cards. And this is through some packing argument that looks very clear to me. But I'm not sure if I have time to go into details. Okay, and surprisingly for this lower bound is actually tight. And by extending the private mean card algorithm, we could also get a K log n error upper bound for private mean card. So this bound is like even tied even to logarithm factors. Okay, so the rest part of the slide is trying to use the packing argument to give the lower bound. So I'll just quickly introduce some intuition. So suppose you want to prove a lower bound for a private algorithm. Now suppose the algorithm is accurate, then it is seen that the outputs for two different inputs should be different. The output for different inputs with different ground truths should be different enough, right? Because like the real value is different, and you want to be accurate. But on the other hand, suppose the algorithm is private, then it is seen that the outputs for two different inputs shouldn't be too different, because you want to make them indistinguishable, right? Yeah. So combining these 2 points, it is seen that on the some privacy level, the algorithm cannot be too accurate. Okay, so I think I should just skip this. So. Yeah, so somehow we are constructing many different exponential size of different inputs, and for each of them, if one card is accurate on one input and it's not accurate on any other inputs, and on the other hand, each different input does not has much difference in terms of the changing edges. So if it is if the algorithm is private, then the output shouldn't be too distinguishable. So, and this gives you a lower bound. Okay, so for brief summary, we figured out the efficient and private algorithms, and together with tight lower bounds for two fundamental combinatorial problems. And it's very interesting to see that even though they are very similar problems, they inherently have very different privacy costs. And for the Multiway card, the tight error bound is n log k, but for K card, the tight error bound is k log n. Okay, and for the open question, our bound for Multiway card is not tight in terms of k. So it may be meaningful to study how to design efficient algorithm to solve the LP with error only n log k. But a more attractive problem to me is that, is it possible to apply the shifting trick I just introduced to design private algorithm for other combinatorial problems, especially those that can be formalized as LP or SDP, such as max cards. Okay, I think that's all I would like to share. Thanks.